All right. Good morning, everyone. Welcome back. So we have a chapter on Milky Way this week. So the chapter we're going to be covering here covers our galaxy, Milky Way. And kind of similar to last time when we had the lecture, I also want to start with the video because it's kind of nice to have a visual understanding of things before we start talking about them. So it's easier to kind of visualize them if you see it in a video. So give me a minute to open that. All right, so this one basically talks about what is our place in the Milky Way. So first talk about a little bit of our solar system, and then goes and talks about a Milky Way Galaxy itself. So it's actually one of the better videos that I was able to find. So I wanted to share with you guys. Let's see what's with the audio. All right, guys, give me 1 second. All right, it should work now.
And our place in the universe. In ancient times, many people had the idea our planet Earth to be at the center of the universe, as stated by Aristotle and Ptolemy's in their Ptolemaic, Aristotelic concept of the universe. According to this model, Earth is at the center of the universe, and all the other celestial bodies orbit around it. Today, lots of people think the same, but is this really the case? To answer this question, let's try to travel in the universe through space and time. We will start our travel from our planet to reach, in the end, the extreme boundaries of the universe. During the 1600s, Galileo Galilei, the famous Italian astronomer, was one of the first people during modern age to have some doubts about the geocentric model of the universe. Thanks to telescopic observations, he was able to demonstrate our Earth is not at the rotation center of planets and the sun, but really it is the sun itself. Moreover, observing planet Jupiter, he discovered that the giant planet is the rotation center for its moons. So Galileo became aware that the center of the solar system was the sun, not the Earth. The solar system is made by a star, the sun, 8 planets, and different types of minor celestial bodies like comets, asteroids, and dwarf planets. Well, the Earth isn't at the center of the solar system. Maybe is the closest planet to our sun. No, it isn't, because it is only the 3rd planet from the sun. The closest planet to our star is Mercury, followed by Venus, and then Earth. The Earth moves around the sun, our star, just like all the other celestial bodies in the solar system do. This implies that the sun, and not our planet, is the center of rotation of the solar system. The Earth takes a year, 365 days to travel its orbit, and its average distance from the sun is 150 million kilometers, which is the measure unit of distances in the solar system known as the astronomical unit, and abbreviated AU. Why do we talk about average distance? Because the orbit traveled by the Earth around the sun is not circular but elliptical. And this means that there will be an aphelion, i.e. the point of the Earth's orbit farthest from the sun, just over 1 AU away from it, and a perihelion, the point of Earth's orbit closest to the sun, just under 1 AU. An alternative way to define the astronomical unit passes through the light time. In particular, we can say the average distance Earth-Sun is equal to about 8 light minutes. This means that sunlight takes 8 minutes to arrive on Earth, so that the sunlight we see at a certain moment is not that of that moment, but it is the sunlight which left from the sun 8 minutes earlier. In other words, if the sun went out, for example, at 2:30 p.m., we would only notice it at 2:38 p.m. Or again, if you could travel aboard the Star Wars Millennium Falcon, it would take you only 8 minutes to travel from the sun to the Earth, when in reality it takes a few years. To give a more concrete idea of the dimensions of the solar system, if the sun were a sphere with a diameter of 14 centimeters, Pluto would be at 700 meters from the sun, like 7 regular soccer.
California homeowners, if you are sick of paying too much money for electric bills,
Sorry,
and you have a
guys.
meter that looks like this in your home, you can get.
Oh wait, yeah, I pay too much.
The nearest celestial body to Earth is the moon, our satellite. To reach it, you should take 3 days off. It's the same time taken by Apollo astronauts to cover the distance of nearly 400,000 kilometers that separate the moon and Earth. But if you had Star Trek's Enterprise and travel at maximum curvature, you would only take less than 2 seconds to reach the moon. Now let's begin to move towards the outer solar system. At a distance of 2 to 3 AU from the sun, between the orbits of Mars and Jupiter, we would meet the asteroid's main belt. Asteroids are those small rocky bodies whose dimensions span from a few kilometers to a few hundred kilometers. They are so small that they aren't visible through unaided eye, but only through telescopes. We could reach asteroids in a few years with a traditional spaceship or probe. Let's move on. We would need around 10 years and 40 AU to fly by Pluto, one of the outermost bodies of the solar system. Try to imagine it in your mind. If you were on Pluto's surface and had to look at our planet, you would only see a pale blue dot. That is the same sight captured in 1990 by Voyager 1 NASA probe, while it was leaving Neptune behind. Around Earth, only the dark vastness of the universe, barely illuminated by starlight. Now we have left behind our solar system, and we are going to enter the interstellar space. To get to Proxima Centauri, the closest star to Earth, we have to cover a bit more than 4 light years. We remember a light year is the distance covered by light in a year in the vacuum and is equal to about 10,000 billion kilometers. Distances begin to become big, since the Millennium Falcon would take more than 4 years, traveling at light speed to reach Proxima Centauri. And the sun? Okay, it's at the center of the solar system, but it is also at the center of the Milky Way. If you continue to travel on board your beautiful spaceship, you will discover it. But it is a very, very long trip, so you will need much patience. The Milky Way is our galaxy. It is an immense group of stars held together by the force of gravity. It has the shape of a flattened disk with a bright core in the center, where the star density is very high, and spiral arms around it. Around the core, there is a spheroidal halo, which extends outside the galactic planet. At this point, it could be useful to introduce the parsec, equivalent to 3.26 light years, to measure the dimensions of our galaxy. So our Milky Way has a diameter of around 30,000 parsec, which are equivalent to 100,000 light years. So if we were back on the Millennium Falcon again and had to cross the Milky Way from one side to the other, traveling at the speed of light, the fastest thing there is, it would still take us 100,000 years to cross it all. Or to put it another way, if you were to send a WhatsApp message to your friends on the other side of the galaxy to decide what to do on the weekend, your message would take about 100,000 years to arrive. Assuming that your friends respond immediately to the message, the response would take another 100,000 years to get back to you. Keeping the same analogy seen before, with the sun represented as a 14 centimeter diameter sphere, our Milky Way would have a dimension of 100 million kilometers. That is equivalent to make 2,497 turns of the Earth along the equator. The galactic halo has a diameter of the order of 30 kiloparsec. and is populated by old stars that are stars with an age double that of the sun. In the spiral arms, instead, there are younger stars, like the sun, located within the arm of Orion, a secondary arm of the Milky Way between the arms of Perseus and Sagittarius. Our star, the sun, is only one of the estimated 200 billion stars in the galaxy. Galaxy with capital initial letter because it is the galaxy par excellence. Our galaxy, in fact, its name derives from the Greek galaxius, the way of milk, referring to an ancient Greek myth for which the Milky Way would represent nothing other than the milk sprinkled out of the breast of the goddess Hera while nursing little Hercules. If it happened to you to find yourself on a mountainside during a clear summer night, looking up at the sky, you will certainly have noticed that whitish milky band that crosses the whole sky. It is the Milky Way. Since the sun is inside one of the spiral arms of the Milky Way, from the Earth we see the galaxy as a streak precisely because we are looking at the galactic plane edge on and from inside it. It's like to try to observe all of our condominium from our flat. We will only see just our neighbor's flat, not the entire condominium because we are in it. But is the sun at the center of the galaxy? No. Its distance from the galactic center is about 8,000 parsec, or if you prefer, 26,000 light years. Our star takes around 250 million years to go along its orbit around the galactic center. This means that since its formation, it's only made around 25 orbits around the center of our Milky Way, traveling at 215 kilometers per second. And it is good that the sun is not in the center of the galaxy, because in it there is a supermassive black hole, Sagittarius A star, a monster with a mass equal to about 4.3 million times the solar mass and an immense gravitational field such that even light is not able to escape. This huge black hole is located in the direction of the constellation of Sagittarius, a constellation observable in the summer for the inhabitants of the northern hemisphere and in the winter for those in the southern hemisphere. Since a black hole does not emit light in the visible band, the same we see with our eyes, it is not visible directly through a telescope, but can be detected through indirect methods. Number one, radiation emitted by the accretion disk around the black hole. A black hole is surrounded by an accretion disk made of matter that orbits spiraling around it. This matter sooner or later falls into the black hole. Before ending up in it, however, it is heated to very high temperatures of the order of 1,000,000 degrees, producing electromagnetic waves of very high energy, such as X-rays and gamma rays. Number two, study of the orbits of the stars closest to the black hole. Studying the movement of the stars in the area of the galactic center, it was noted that they seemed to rotate around nothing, because apparently there was no visible celestial body in that area. Studies conducted by research groups led by astrophysicist Andrea Ghez and Reinhard Genzel, who won the 2020 Nobel Prize in Physics together with Roger Penrose, over the course of many years, have shown the existence of a celestial compact body at the center of our galaxy, right in the area where the black hole Sagittarius A star is located. And what about the Milky Way? Is it at the center of the universe? Even in this case, the answer is negative. The Milky Way belongs to the local group of galaxies, with a dimension of 10 million light years, or 3.1 MPC, megaparsec. We remember that 1 MPC is equal to 1 million PC, and that 1 PC equals to 3.26 light years. The local group includes more than 70 galaxies, most of them of small size. The center of mass of the local group is between the Milky Way and the Andromeda Galaxy, M31, and the local group, together with the Eridanus cluster, Fornax cluster, and Virgo clusters of galaxies, belong to the local supercluster with a diameter of around 100 million light years. It is thought that our universe contains around 200 billion galaxies, along with 200 billion stars. Can you imagine that with satellites, space probes, and telescopes we have explored so far? Only a very little percentage of the universe? In conclusion, our Earth is not at the center of the galaxy, neither of the universe. Only a small...
All right, so we pretty much got the gist of it. All right, so again, I wanted to show you guys that because some of the things we're going to talk about is kind of difficult to visualize, but This video, had a nice, let's say, graphics, high definition. So it was, easy to, maybe it will be easy for you guys to visualize once we start talking about in greater detail about some of those things. All right, so let me then open the PowerPoint slide. And start basically covering our Milky Way galaxy. So first part is going to be discovering the galaxy, and basically how we learn that, there's more stuff than, let's say, we can see. Remember, some of the things, I mentioned before, that there are a lot of clouds of gas and dust in space that light cannot go through. So, and when we see patches of sky where it's completely dark, doesn't necessarily mean that there are no stars over there. Maybe that basically that region has a lot of, cloud of gas and dust that doesn't allow us to see what's behind that. Eventually, with telescopes that go beyond the visible range, right? So let's say radio telescopes, or let's say X-ray telescopes and things like that, we are able to see some of those, let's say, hidden parts of our Milky Way galaxy, or of universe itself. But in terms of, you can see that this chapter, you can break it down into 3 parts. Obviously, today we're going to cover some of it and continue on Thursday and finish the rest. So we're going to talk about the Milky Way galaxy, how it was discovered, what are the first early models of the galaxy, and then our modern, let's say, take on Milky Way galaxy, and looking at some different parts of it. And at the end, we're going to talk about center of the galaxy, and as the video suggested, that the center of our galaxy is a supermassive black hole, and which actually seems to be true for most of the galaxies as well. Most of the galaxies that they're big enough to have a supermassive, black hole at the center, they do so. There are, let's say, a lot of small galaxies that might not have, a black hole at the center. But what we can see from, let's say, using the Hubble telescope, all the galaxies, most of them, do have a black hole at the center. And there are, let's say, we're going to talk about, the different type of galaxies in the next chapter. But at this point, once we understand what the Milky Way galaxy is, some of the specific properties of the galaxy, then most of them are maybe different in terms of their shape. Some are spiral, some are elliptical, but in most sense they are similar to the Milky Way galaxy in terms of their properties. All right, so let's talk about, okay, so this is one of those, let's say, images that you can see, right? In the night sky, you can see that, so there's like the band that, we call Milky Way. And there's another one right here. So you can see, right, this region here is basically what we have, toward the center of the Milky Way. And by the way, this picture is taken by me. I took this picture about a month ago. We went to Joshua Tree, and if you ever have a chance, just go there and look at the night sky. It's just beautiful over there. So I use long exposure photography to take picture, and here you can clearly see that this is toward the center of our galaxy, and that band basically includes lots of stars. So we're going to talk about that, and we're going to talk about, let's say, why we see sort of like, let's say, kind of like the band like that, and why there are more stars toward the center. All right, so one early model that we had for the galaxy, and there are many different ones, going back, to in ancient times. It's just, when we talk about, let's say, from, early Greeks, right? Remember, so for them, it was geocentric universe. So it was pretty much the Earth at the center of the universe, and everything else is just around, around Earth, going around Earth. And that was, obviously not accurate model that eventually was changed into a Copernican heliocentric universe. But still, up until, you can see, around 1785, so late 18th century, most of our models involved, let's say, our solar system or our sun to be at the center of, what we knew at the time was the universe. Kind of jumping ahead a little bit, what we know now that we are in a Milky Way galaxy, and there are a bunch of other galaxies, like billions of other galaxies, is actually not a very old, let's say, understanding of the universe. So up until 1920s, I'm talking about 100, less than 100 years ago, we didn't know about other galaxies. We used to think that, Milky Way is the universe. This is what we see is what there is. Hubble was actual scientist, and in 1920s, he used a telescope to discover, not necessarily discover, right? To realize that some, objects that we see in the night sky don't belong to our galaxy. And those are actually so far away that can be considered as separate galaxies. So pretty much he discovered Andromeda Galaxy, or he figured out that what you're looking at is the Andromeda Galaxy. Then from that, obviously now we have the Hubble telescope, which takes pictures of, billions of galaxies in one shot. So, hundreds of, thousands of galaxies in one shot. The idea is that now we know that there are many galaxies, but we didn't know until, 1920s. So 100 years ago, less than 100 years ago, we still used to think that Milky Way is the universe. So when we go about, 300 years back, so you can understand that their understanding of, universe was even more limited. So, but still at this time already, there were a lot of, natural philosophers. We didn't call them scientists back then yet. So they started, let's call them astronomers, more appropriate. So they started trying to figure out, our place in the universe. So and William Herschel is one of the first ones who tried to map the sky. So basically, obviously, the night sky, because during the day you can't really see much. So he, with his sister, William Herschel and Caroline Herschel, they pretty much recorded every celestial object they could see in the skies, and they ended up with the map that you see in front of you there. So more or less, their map, basically the map of the universe, right? That's what they called it. So it still kind of placed the sun at the center, so as you can see, right? And there are, some regions, for example, see those regions over there. It seems like, either they couldn't map or something like that. Well, those ones are, what we can right now understand is the region of clouds of gas, that what we call molecular clouds. So those clouds are just like, imagine, right? So if it's a really, let's say nice sunny day, so that you can see the sky, you can see the sun, you can see the, let's say airplanes, right? But when it's a cloudy day, then you cannot see the sun, you cannot see the airplanes at the, that's because, basically the clouds pretty much block everything. So we can't see the sun, we can't see the airplanes because of the, let's say clouds that we have. Same thing with the molecular cloud. So if you have a molecular cloud in space, those are, clouds that can be as big as, 10, 20 times our solar system. And they basically block everything that is behind them. Okay, so that means it could be a lot of stuff over here, but if there's a kind of like a cloud here, it will, not allow us to see what's behind. Now, that's basically works at the visible spectrum. That means, obviously in 1785, Herschel was using a telescope. There was a telescope at the time, but that telescope was only, optical telescope. And with the optical telescope, you cannot see beyond or through those, molecular clouds. Now we have radio telescopes, and the radio telescopes do allow us to see beyond, what's behind those clouds. So the radio waves can go through those clouds. They can penetrate those clouds and reach our telescopes, and we can pretty much map out all those regions as well, but not with the optical telescopes. All right, so this was pretty much, our first more or less scientifically accurate, let's say, map of the universe. And scientifically accurate because the brother and sister, Herschel brother and sister, they actually were, taking many, data, they took a lot of data, all the observation, and they mapped it out. So this was highly accepted at the time, and, for, maybe hundreds or so years, it was considered to be, let's say, more or less the model that they would use. Obviously, some modification here and there, but eventually, we were able to, maybe in 100 years or so, 150 years after this, be able to get, I'm talking about relative to 1785, get much more accurate, measurements of things. All right, so you can see that this is kind of, the shape of the Milky Way was believed to resemble a grindstone with the sun close to the center. Again, so in the video, hopefully you guys were able to catch the part when they talk about why it's called the Milky Way, right? So it's kind of like the Milky Way in terms of the resembling the milk. So, but in terms of the Cyril name, there's a Roman name, there's a Greek name, thing like that. So we kind of call this a Milky Way, mostly coming from the Roman version of that. All right, so here's the thing about our galaxy. As you can imagine, right? So for us to have a picture of our galaxy is basically impossible. We cannot have, let's say, if I show you a picture and say, here's Milky Way Galaxy, obviously you have to understand that's not our galaxy. We cannot have the actual picture of our galaxy because we are in it. We cannot take a picture of the galaxy, the Milky Way Galaxy, because we've never been outside of the Milky Way Galaxy to take a picture. Kind of similar to just like the video suggests, right? Imagine you're living in an apartment building and you are in one of those apartments and you are trying to figure out what your apartment looks like without ever leaving your apartment. So you can look through the windows, you can kind of see what's going on, a little bit from outside, but let's say you cannot really see the entire building. So, but what you can do here, you can look at the building in front of you, the next to you, and kind of, figure out more or less the size, relative size and structure of your building. So by kind of comparing it to the other things that you see in front of you. Same way, what we do here is with our Milky Way Galaxy. So we can, so for example, this is Sombrero Galaxy. This is a picture of Sombrero Galaxy because we can see this with our telescopes, where we can take a picture of that. And it's pretty much actual picture of the galaxy. Now we can then have actual picture of pretty much all the other galaxies except Milky Way. And then by studying Milky Way from within, then we can compare it to other galaxies and then have a rough idea of our own galaxy. So for example, this Sombrero Galaxy, you can see, right? We see a gas and dust absorbing light in other galaxies over there, right? So there's a dark dust lane when we see a galaxy adjust. So we can see, right? So that what we can have here is sort of like, let's say, a disk like this, and then sort of like a central bulge. Okay, so that's basically, we can see a galaxy from that. And when we see all the other galaxies, and when majority of the galaxies kind of similar, they have a disk and they have like a central bulge, then we can assume that, there's a highly likely that our galaxy have the same, same structure as, pretty much, for example, Sombrero Galaxy. For example, here's a picture of NGC 2997. So generally NGC just basically refers to a catalog, specific catalog. 2997 is the, let's say, number of that, celestial body that we have. For example, this is a spiral galaxy, and we can see that it looks a little bit different, but still there's a, sort of like a central bulge. And, so this is kind of looking from the, in the plane. So one of the things we can have here is because we can take pictures now with the Hubble telescope of billions of galaxies, we can we can see that, you kind of move around and you can see those tons of galaxies. We can see galaxies in different ways. We can look at them edge on, we can see them, face on and things like that, and be able to really have a good understanding of a structure of different type of galaxies. And especially in let's say next chapter, when we talk about galaxies, we can see that all the galaxies, can be put in a way more or less about, three main categories: spiral galaxies, elliptical galaxies, kind of like, have an elliptical shape, or some that are, too irregular to be either elliptical or spiral. So since elliptical and spiral, basically about, 80% of all the galaxies that we can see, those two categories, then we can try to understand that, our Milky Way should be either elliptical or spiral. So when we study all the elliptical, when we study all the spiral galaxies, then we can say, okay, our galaxies looks much more like a spiral galaxy that we are, all the spiral galaxies we're studying. So most likely it is a spiral galaxy. Then as we take it as a spiral galaxy and start studying further, we can then, have a confirmation on that as well. All right, so here's an example of a picture of toward the center, right? So like, let's say, but you can see that in terms of what we have, there's a galactic plane, and there's a galactic center. Okay. It says the structure is hard to determine because we are inside. Distance measurements are difficult. Remember, one of the hardest things is to measure the distance to celestial object. So remember, we were talking about how we get the measurements of the distance to a star, and that was one of the more complicated things, because we had to, I think, I might be wrong on this, but I think distance was equals to 10 raised to the power of this is a absolute magnitude minus visual apparent magnitude minus 5 divided by 5. It was something like this. That means we need, we need at least two things, right? We need to know what is the apparent magnitude, what is the absolute magnitude, and then we can then measure the distance. So, and distance is one of the hardest thing to find, because, let's say, it's not like you can take a ruler or a meter stick and then go start measuring things. Apparent magnitudes are a little bit easier, because apparent magnitude is how they appear to us. But absolute magnitude, so like, let's say this absolute visible magnitude, right? That's basically a much harder, because you are trying to determine what's the actual energy production of a star or of an object, let's say. So that's a little bit more difficult, but we talked about the ways that we can actually do that as well. And eventually those are the ways that were used to find a little bit more accurate structure of our Milky Way galaxy. We're going to talk about that, but that's one thing we have, right? So the distance measurements are difficult, and our view toward the center is obscured by gas and dust. Okay, so using the radio telescopes and X-ray telescopes and things like that, that's actually quite a recent, let's say, addition to our arsenal of, let's say, tools that we have, because about 100 years ago, when we were just trying to understand, the structure of Milky Way galaxy and what's going on, we didn't really necessarily were using those type of tools. It was mostly optical telescopes, and with optical telescopes, you are restricted to what you can see directly, and any type of gas and dust, which basically part of the those molecular clouds that I was mentioning, right? So we call them interstellar medium, right? They can block the light, and we cannot see what's going on, behind it. So that's kind of like that was the problem initially. All right, so now in terms of then what we do here to find distance in Milky Way, we want to look at the biggest and brightest things. Okay, and that's because the smaller ones are very faint, and they're not very easy to let's say get the actual let's say the absolute magnitude and things like that. But stars that are very big, very bright, well, those are easy to kind of, let's say, easy to absorb, because remember, one of the things we can get here is we can get the temperature by just looking at the color of the star, right? And using the temperature and things like that, we can, get, remember, for us, absolute magnitude was pretty much directly proportional to the, remember we talked about luminosity, right? Directly was proportional to the, temperature or the color of the star. Those small stars are very faint, so it's even difficult for us to figure out the actual color because they're so faint. So to understand in terms of finding the distance, let's say, for example, if you're right here and you find the distance from this point A to point B, then what you do, you find a very bright star, O and B. So then you look at how it appears to you, and then you look at its temperature, its color, to figure out the absolute magnitude, and then you can use that distance modulus equation to figure out, distance to that object. Okay, so give me 1 second. Something happened here. All right, sorry, I had some technical difficulty. All right, so we look for bright objects or B stars. Remember, O is the brightest stars, right? Most massive and the brightest stars. So big object. So H2 regions. So H2 regions is basically regions where there, H is a hydrogen. So, but in terms of basically some kind of bright object that is easy enough for us to make observation. And obviously you can use IR and radio, which means IR is infrared or radio waves, because visible spectrum, right, or visible optical spectrum is limited for us. Our telescopes cannot penetrate through those, clouds of gas and dust. Radio waves and infrared can do that, and modern telescopes allow us to, let's say there's a specific designated radio telescopes that can help us do that. All right, so, and one of the important things that were actually used in, let's say, early 20th century to figure out the distance to the object and eventually map out the our Milky Way Galaxy were Cepheids. So those are Cepheids are the stars that pulsate. That means they change their shape and temperature at the specific through a specific period of time. Excuse me. That means so that means they can let's say start increasing and then starts decreasing, and they do that at a very specific, let's say, interval of time, so we can map it out in terms of measure the how long it takes for it to increase and how long it takes for decrease, so that we can calculate what we call period. And then from the period of the pulsating stars or Cepheids, we can figure out their intrinsic brightness, their absolute magnitudes. Okay, so now one thing we have here is the scientists started looking at star clusters, because in the star clusters then you can have the brightest stars, and usually star clusters is a little bit above the, let's say, the central disk, so that it's easy for us to kind of see them. There are two types of star clusters: open clusters. So open clusters usually young stars, because those are probably a region that used to be a cloud of gas and dust, but then it was changed into forming new stars. So those stars are open, means that they are not too close to one another, and they're not very strongly bound to one another. So they can still get closer to one another, or some of them can move away from one another. But for example, here the open cluster in the Perseus, so this is an example of that. So open clusters allow us to basically find some of those brand new young stars. And sometimes some of those brand young stars are very bright and generate a lot of light and a lot of energy. And there are also globular clusters. So usually globular clusters, we're going to see it's in the halo of our galaxy. And they are very, very old stars because open clusters as I said, right, those are the regions where there were very recently, there were a lot of clouds of gas and dust. And all the clouds of gas and dust is the raw material that was used to create or to make those young stars. So there could still be a plenty of gas and dust available in those regions. Globular clusters are the regions where there are almost no clouds of gas and dust. That means we can assume that pretty much no new stars are forming there. So all the stars are, have been around for a long time. So it could be hundreds of millions of years or billions of years. Some can be as much as 10 billions of years. So that means those globular clusters, you can see are mostly in the halo around the galaxy. So to understand and let's say, remember, our goal here is to do this, right? So to look around and try to understand how big the Milky Way galaxy is. So we want to find the distance from one end to another. Well, to do that, we need bright stars. And bright stars we can find in clusters like this. So there are two clusters, open cluster and globular clusters. Okay. So then if you look at the Milky Way, obviously this is our understanding, let's say approximately what we think the Milky Way looks like, right? As I said, right? So we can never sit and 100% say this is, how the Milky Way looks like. So obviously we have very accurate, approximations. So that one of those approximations that it's a spiral galaxy like this, where relative to its center, which is basically some kind of nuclear bulge over here. We're going to talk about later that there's a, supermassive black hole over there. So to go from one end to other end, let's say this is point A, this is point B, to find, let's say, the diameter of our Milky Way galaxy. Well, obviously what we want to do here is we want to, compare, right? So let's say relative to where we are, which is right here, find some kind of star that is here that is extremely bright. So measure the distance to that side. Find something here that is relative to bright. That means measure the distance from there, measure the distance here, find something here, find something there. So measure those distances, and then we can more or less figure out some kind of, let's say we have enough information to figure out some kind of structure, right? Let's say a physical structure of our universe. So in terms of then what we can see, right, this is face on at the top, and at the bottom is basically edge on. And what we can see here is there's a, so basically if you kind of take this and turn it 90 degrees, so then you have basically this disk over there. So that's the disk, and it's a very thin disk compared to the size of the galaxy. So things like this, it's similar to like a thin crust pizza, not a regular pizza, but a thin crust pizza, probably even thinner than that. So it could be very, big, but the thickness is very, very tiny compared to that. So on average, it's about 30 kiloparsec. That means this, from one end to the other end, that means the diameter. But this thickness here is, and remember, kilo stands for 1,000. So it's things like this, like 30,000 parsec and things like this. Then the disk is, let's say, roughly 30 parsec. You can see what a big difference, right? So what a big difference compared to the entire diameter and the thickness of that disk. Okay. All right. So now we can also see this region over here. This is what we call the halo. So, and most of the globular clusters are there. So those globular clusters are within those halo. And open clusters usually, happen around this region. So much closer to the disks. Okay. So much closer to the disks, and we can then use them to basically map out close, and the far away parts of our galaxy. Okay. And also important to mention that that's actually where the our solar system is. So our solar system is not the center of Milky Way Galaxy. It's actually it's about 2/3 relative to the center, and let's say this side over here. Um, so it's not necessarily center of we're Earth is not the center of the universe. Sun is not the center of the universe. We're even not at the center of our galaxy, and galaxy is not the center of the universe. So basically, we're um, just an ordinary planet around the ordinary star, ordinary galaxy, and our galaxy even it's ordinary galaxy. There are much bigger ones. There are much brighter ones, and even Andromeda Galaxy, which is our neighboring galaxy, that in a way it's in a collision course with our galaxy. It's actually much bigger than Milky Way Galaxy. Very similar in structure, but bigger. All right, so you can see that those are disks, and then you have the nuclear bulge, and you have then the halo. Those are then the globular clusters. Okay. Clean up my writings over there. All right, so now what we're going to do here, we're going to talk about what we call population one. So let's say the type of stars that we have, right? So like if you categorize them, you have a population one, which is young stars with heavy elements, metal rich. Now, one of the things we have here is then we have a population two, and remember the young stars, as I said, right, usually found in open clusters. So open clusters is generally on the disk of Milky Way Galaxy. There are regions where there's still formation of new stars. That means you see almost no new stars in the halo. You see very few new stars closer to the center. That means in this region also there's almost no new stars. Most of the new stars are these regions over here. That means where you have those in a way, like these are the regions where you have new stars forming. Okay, so those are the regions where new stars are forming, and what we get here is an open cluster. That's mostly where the new stars are, and then there are heavy elements present in let's say in the composition of those stars. Population two, we call them those are for the old stars. The metal poor located in the halo, globular clusters, and nuclear bulge. That means closer to the let's say the center of our galaxy and in the halo. Now, there's also a very good reason why that's the case, because population one stars have heavy elements. Okay, that's because they're new stars. Well, population two stars, they don't have any metal poor. That means it's basically they have some, but not as much as population one. Again, those stars are very old, and if you remember, I mentioned several times already in previous lectures that initially when the universe formed, we had mostly hydrogen and helium. There were very few heavier elements was available. So this population two stars, which are old stars, they were basically formed at a time when there were very low supply of very heavy elements. So that means, when they were formed, it was hydrogen, helium mostly, and maybe very, very little of anything else. But then, let's say, including those globular, let's say clusters, they always, when the stars are forming, you always have really big, massive stars sometimes forming, and then really, small stars. But most of the time, what you have here, you have more or less kind of like, let's say, a sun-like star, like let's say, basically somewhere between half a solar mass to about 3/4 solar masses. And the stars that we more or less see right now in the halo are somehow like that. That's because the very big stars, they die very quickly, as we talked about last time. But when they die, when those stars die, well, they explode. And before they explode, remember, we talked about how very massive stars have to produce a lot of, let's say, energy to keep or surviving, right? And some of the type of elements that they produce are heavy elements. That means when the star is producing energy, like let's say if it's a very massive star, it goes from hydrogen to helium, from helium to carbon, then to oxygen, then to phosphorus, then to nitrogen, and all the way to iron. Then basically that's when you have too many very massive stars dying eventually, right? Then basically you can say that they have generated a lot of heavy elements. So when they die, they explode, and this explosion sends out shockwave to the molecular clouds when that starts producing new stars. But those shock waves basically generate a lot of heavy elements that are pretty much pushed toward those clouds. And when the stars are forming new stars, then that means now they don't not only have supply of hydrogen, helium, but also a lot of heavy elements that were generated inside those dying stars. That means more stars die, more heavy elements are present to the new stars. So that's why most of the new stars are, heavy element rich, because, as the time goes, more and more and more stars going to have an even, higher level of, let's say, heavy element present in their composition. So that's how we can know, right? Which one is a young star, which one is an old star, by just looking at the composition. The ones that they have very little, let's say, heavy elements. And remember, those are something we can easily figure out, right? So we can look at the light coming from the stars. We can put this in a spectroscopy and see what type of elements present in the atmosphere of that star. So if there are almost no, let's say, heavy element present, then we can determine the age of that star. So that's what population 1, population 2. Just understand the difference between young stars and the old stars. And it's mostly in terms of the amount of metal that we can find inside, and also where we can find them. If we find a star in a halo, most likely it's a very old star. And if we find them in a disk, then most likely it's a new star. And then heavy element basically verifies that for us. All right, so that's kind of what we have. So young stars, heavy element, metal rich, located in the spiral arms and disks. So our sun is one of them. Population 2, heavy elements, metal poor. That means they don't have, because they were made, right? Those stars were born when there were very little metals available. So then what we can do here is we can kind of like put it in a category like this. So you have population 1, population 2. There's obviously always, you can have a subcategories, right? So there's extreme and there's intermediate. So for example, one thing we have here is, for example, metals, right? The percentage of the metals present. And you can see that population 1 is here, and then you can have up to 3% heavy metals, right? Or 1.6%. So when you have 3% or more, this is known as the extreme population 1, because you can probably think of like they are even younger, because as time goes, as I said, right, more and more heavy, let's say, metal rich, let's say, materials is available. So usually they are in a spiral arms. The shape of their orbit is the circular, and they're 100 million years old or younger. Okay, and then intermediate population 1, they're usually then in the disks. And they have roughly 1.6% or less, and they're slightly elliptical orbit rather than a circular orbit. And you can see they're about 200 million to 10 billion years old. So that's why extreme population 1 stars are much younger than intermediate ones. All right, so then you go to population 2. So for population 2, then you have 0.8%, so less than 1%, so 0.8%. That means 99.2% is just hydrogen or helium, and only 0.8% is heavier elements. Or you can have extreme where it's even less than that. even less than that. So these guys are 2 to 10 billion years old. This one 10 to 13 billion years old. Okay, and generally the stars that are in disk or in spirals, they go around the central, the central bolt in a circular or liberal elliptical orbit. But the population 2 stars that are in a halo, for example, this guy over here. So this can kind of go something like this, highly irregular elliptical orbit. So it can kind of go like this and come back, right? So it just basically highly elliptical orbits, and it can constantly also change that. All right. So important to understand the age difference between them. All right, any questions?
Now good.
All right. So let's talk about here. The way then here in terms of this is what I was just mentioning, the orbital motion. So if you talk about, let's say, the center of our galaxy, most of the stars that are on the disk or spirals, they go nearly circular or elliptical orbit, like our sun. So remember, it takes about 250 million years for our sun, which is right here, sort of like to go around our galaxy, which is kind of true for everything in the universe. Everything is in motion. See, the moon goes around the sun. So moon goes around Earth. Earth goes around the sun. Sun goes around the Milky Way, center of the Milky Way Galaxy. Well, the Milky Way Galaxy itself, along with some other galaxies nearby, go around relative to what we call like a center of mass of that system. And then all the universe, or everything basically in constant motion. So now here, an example of how the stars, there are population 1 stars move around relative to the center of our galaxy. And this is then population 2 stars. In a halo, they're highly elliptical orbits and randomly oriented and things like that. So still, let's say they're all bound to the center of the, Milky Way by the gravitational force. Okay. All right, guys. So I'm going to go ahead and stop on this today. So we'll continue finishing a little early today. So we're going to continue this on Thursday. We're going to be finishing this chapter on Thursday, and that should give you enough time to, finish the homework. All right, guys. So that's it for today. Have a good rest of the day. I will see you in, a couple of days. All right,
Cool.
care.
Thank you, Professor.
Professor.
Good day.
Thanks, Professor. See ya.
Bye-bye.